Today we want to talk about enthalpy and the heat of formation. Heat of formation, remember, is the change in heat that accompanies the formation of a compound from its elements. And we've done calculations with heats of formation before when we were figuring out the entire heat of reaction of a particular chemical reaction. But I want to show you some problems, different types of problems that you might encounter in this with this concept. So when you see heats of formation values and you see that little zero up the top right here, that indicates that the reaction was carried out under standard conditions. And those standard conditions are 1 atmosphere for pressure, 1 molar for concentration, and standard temperature in thermodynamics is 25 degrees Celsius. Now that differs from standard temperature in the gas laws, which is 0. I wish they'd make it the same for both, but they don't. So we have to remember that standard temperature is 25 degrees Celsius, which is about room temperature, so it kind of makes sense. So all of our values are determined at 25 degrees Celsius. So if they don't tell you the temperature and they're giving you table values for this, it's got to be at 25 degrees Celsius. So also remember, delta H for any element in its standard state, and remember that includes our diatomic elements as well, is 0. So don't forget about that because they won't give you that value. They'll expect you to know that. So it's asking us to calculate the heat of formation. Now, we've calculated heat of reaction, the total before, but this one is wanting us to calculate the heat of formation for just ammonium perchlorate. So if we find ammonium perchlorate down here, that's going to be our X value, okay? Notice that it has a 3 in front of it, so we're going to be looking for that, and we have to keep in mind that when we have these heats of formation, we have to multiply those by the coefficients that are in the balanced chemical reaction. Remember that aluminum is 0 because it's a free element. It says down here that aluminum oxide is negative 1676, that aluminum chloride is negative 705, that the nitrogen monoxide is 90, but there are 3 of them, so make sure you multiply that by 90, and that water is negative 242. 6 of them, so negative 242. Now, something else that's very important, and this is what people often miss, because you'll see this chemical reaction, and you'll sit there going, but they didn't give us a total. They didn't give us a total. Yes, they did. Right here in the chemical reaction, they gave us this value. Now, remember, it's on the right-hand side, so remind yourself about what that means. It means it's exothermic, because heat is being given off, which means pull that value out of that reaction and it's negative 2,677 kilojoules. So watch for those kind of things. Remember, if the value's on the left, it's going to be positive because it's endothermic. So it does give us a total heat of reaction there. So let's set up our equation. Remember, the equation is that the heat of reaction, the enthalpy of reaction, is equal to the sum of the products minus the sum of the reactants. So we know that the heat of reaction is negative 2,677 kilojoules. Remember that we will be so much better off if we remind ourselves to keep those in brackets until we get those calculations. So we've got for the products negative 1676 plus a negative 705 plus 3 times 90 plus 6 times negative 242. And we're going to be subtracting our products, which is simply going to be our 3x since aluminum is 0, minus 3x. So that ends up being negative 2,677 kilojoules. If you multiply out and add everything inside those brackets, we end up with a negative 3,563 minus our 3x. Now, I do not like working with negative x values, so I always change things around. What I'm going to do is move the 3x. I'm going to add 3x to both sides, When I add that 3x to both sides, it's going to cancel over here and appear over here. I'm also going to add the negative 2,677 to both sides, which is going to cancel it on this side. And if I add 2,677 to the right-hand side, I end up with negative 886 for my value. That's for 3x. So x, which remember our x value was the heat of formation of our ammonium perchlorate, is equal to negative 295 kilojoules per mole. And since this is for a specific reaction, per mole reaction. Okay, so that's just a different way you might see a problem. Let's look at this next one. It says the heat of formation of acetic acid is negative 876.1 kilojoules per mole. Show a balanced reaction for the formation of this substance from its elements. So this is, people get confused by this all the time, but all we're doing is taking the elements in their standard states, which is going to be carbon, hydrogen, now standard state, so remember hydrogen's diatomic, oxygen also standard state, so it's going to be diatomic, and that's going to form CH3COOH. Now balanced, we're going to need 2 of our carbons and we're going to need 2 of our H2s to get that balanced. Now it doesn't really say to put it in, but I'm going to go ahead and put in the heat value. Since the value is negative 876.1, where's that going to go? On the right-hand side. Remember, we don't put negatives in chemical equations, so we're adding it to the right-hand side. That shows us it's being given off. So plus 876.1 kilojoules. Generally, they don't put the per mole on there in the chemical reaction. So is this reaction endothermic or exothermic? Well, because of that negative right there, we see that this is an exothermic reaction.